Hello and welcome to the NPTEL online course on microelectronics devices circuits. In our previous file or previous, we have understood what is known as the small signal model of MOS device, wherein we understood what is known as a hybrid pi model and what is a T model. So, for both MOS device. So, why was it important? The reason was that whenever you encounter a MOS device in a circuit, you can replace it by that equivalent circuit model, and then calculation of various gains and output gain, current, impedances becomes much easier. We have also seen that in the previous example or the previous slide that your MOS device is basically a voltage controlled current source, right, and therefore, by using an external voltage source which is gate to source, my drain current flowing through the device can be changed, right. What we will see today is basically the various configurations of amplifier, and therefore, the name of the topic of today's discussion is basically your common CS, CG, CD amplifier configuration. CS primarily means common source, CG means common gate, and CD means common drain. They are also known as source grounded, gate grounded and drain grounded amplifier configurations. So, these are all actually an amplifier which is there with us. So, let us see the first. So, what will be the outline of my talk? The first thing which we will be studying is basically my common source amplifier, which is basically also known as source grounded. This is the most commonly used amplifier design across the world, and for reasons we will discuss later on. We will see the various characteristics of this amplifier, which means that we will be looking into the various output characteristics of this amplifier. We have seen in our previous discussion, if we apply a source resistance, right, how does my CS amplifier change, or how does its output characteristics change? After we have understood these three important points regarding CS, we go to common gate and then source follower or common drain, right, common drain also referred as a source follower, and there are certain reasons why we study CG and CD, but the most commonly used amplifier is basically a common source amplifier, right. Common source amplifier is this is the diagram of a common source amplifier, right. This is the diagram of a common source. You see here you have a NMOS device which is this one. So, this is the active device, this is your output resistance of the input signal source. So, this is the signal source which is there with me, right. So, assuming that I have already DC bias state, which means that I have already fed these devices with an external VDD supply and source supply and biased it at saturation region, so that it works as an amplifier. This V signal is a small signal input voltage which I am giving to the MOS device, and R signal is basically my resistance offered by the voltage source. So, a voltage source, please understand, output impedance is very low, but in reality you might get some amount of resistance offered by it, and that is given by R signal, right. So, R signal therefore comes in series to V signal, and V signal is the input voltage which you give. Then this RD is the load resistance or external resistance which you see from our external world. So, you see the effective V in shown in this blue diagram, in this blue curve, is basically the V in is the input voltage. So, you see depending on the value of your R sig, right, and this resistance Rg or Rd, some part of V sig will appear as Vi. So, not all of V sig will appear as Vi, or it might appear, but you will have a voltage divider network, and therefore not a part, we will see later on that a part of V sig will appear as Vi. So, that is nothing but VGS, because source is grounded, whatever gate voltage you give will be basically your gate to source voltage. That will generate a current ID. That current ID multiplied by this RD is basically the voltage drop V0 which you get, and therefore, that will be the output voltage which you see, fine. With this knowledge we have gained till now, let me therefore do a matching of 1-to-1 matching between the actual circuit and the equivalent circuit model. So, what I do, I replace this MOS device here, this device here, by its equivalent circuit which you see is this one. Please understand, it is very important to how you are replacing it. You are replacing it, why? Because please understand that GM-VGS, this one is nothing but the current source, which is drain current of this MOS device. So, I have the MOS device whose applied input voltage is approximately equals to VGS. Why? Because input voltage I am giving here, gate to source voltage is equal to input voltage, and therefore I get GM-VGS is the drain current. We have also understood in the previous, when we are discussing the small signal, was that I will always have a RO, which is the output impedance of the device, by virtue of the fact that your output will be slightly CLM'd. So, you will have always a channel length modulation phenomena, and therefore, at this point if you want to find out del I V del I D, you will always have a R0 which is not equal to infinity, but typically a relatively a large value will be there, right, and that is what is R0 here. So, this R0 primarily comes out because of CLM, which means that assuming that my device which is a MOS device here is behaving like a non ideal current source, and therefore I will have this R0. This RD is the applied drain resistance in the output side or the load resistance, whatever you see. So, the effective resistance seen by the output world is nothing but RD parallel to R0, fine. This is RD parallel to R0 which we see, right, and therefore, this is RD parallel to R0. So, let me just discuss with you that how will I look into the same fact. So, let me draw for you this diagram. This diagram, if you look very carefully, then I will have signal here, right, I will have signal here, I will have R signal here, right, and then I will have GM-VGS, right, as the current source, and then I will have R0, and then I will obviously have RD with us, right. This is what we have learned till now, and this is what you get. So, this is your V sig, this is your R sig. Please understand, therefore, your input impedance is actually infinity. Why? Because your current your gate current will be 0. Why gate current will be 0? Because see, wherever inserting a current or voltage, you are inserting onto the gate side of your MOS device. The gate is separated from the channel by a oxide layer or a thick oxide layer, right. This oxide layer is primarily, if you look very carefully, is a dielectric material, of course, and therefore, I would not expect to see any current flowing through the MOS device through the as a gate current, and therefore, looking from the gate side, which is the input side, your impedances will be very large. So, your Z in will be typically infinity, ideally it will be infinity, so large, and therefore, I keep it open, input side is kept open, right. This is kept open, this is the input side and this is my output side, input side is kept open. With this knowledge, let me define what is, there is a term known as what is known as unilateral, and then you have another type of amplifier which is non-unilateral. The meaning of unilateral is that if there is no feedback between output and input, which means that the effect of output impedance, right, does not load your input impedance and vice versa, then we define that to be as a unilateral. If there is a feedback loop which tells me that no, if I start loading the output, loading means I increase the value or decrease the value of your load resistance, then your impedance input impedance also changes, we define that to be as a non-unilateral amplifier, right. So, we have two types of amplifiers typically, amplifier, and this is one is a unilateral amplifier, and we have a non-unilateral amplifier. So, if I have a non-unilateral amplifier, it means that if I change the output, I would expect to see a change in the input by some closed loop control, right, whereas a unilateral amplifier, both are totally different. So, as you can see, since my input impedance is infinitely large, actually my input does not talk with the output directly, and as a result you will actually see that there is no change in the value of your input impedance because of the change in the output impedance. Now, with this knowledge, let me therefore start doing the derivation for the gain for the CS stage design, and let us see how it works out. We discussed just now that of course, your gate current will be 0, and therefore, your input resistance will be approximately equals to the gate resistance, which means that whatever your input resistance is there will be equals to gate resistance. Therefore, I can safely write down Vi equals to V sig, right, Rg upon Rg plus R sig. Why? Because Rg is a resistance which is the gate resistance which you see. I am assuming it to be infinity, but let us assume that it is not infinity at this stage and it is having a finite value, then we define Vi to be equals to V. So you see if Rg is infinite value, right, if it is infinite value, then this denominator will be actually equals to just, if you look, denominator will be just Rg by Rg. So Rg will cancel and Vi will be equals to V sig, right, and that is true also. That means if your ideally if your device, MOS device would have shown you an infinite resistance, my input signal and my actual signal given by the voltage source will be exactly equal to each other, but since they are not, I will have a voltage divider network here, and therefore gives me a value of Vi here, right. But since my Rg, as I was discussing with you, since Rg is much larger as compared to R sig, I will automatically get that Vi is approximately equals to V sig, right, and therefore we can safely write down Vgs is approximately equals to Vi, right. So whatever you give the Vi, that will be equals to Vgs as such, right. With this knowledge we have already, if you remember from our previous discussion, that the AV voltage gain was equals to Gm times Rd. With that knowledge, let me see how it works out. That let me suppose I want to find out VO, output voltage, then it will be minus Gm times, right, Vgs times Ro parallel to Rd parallel to RL. RL is the load resistance, there will be some load resistance in the output side, and let me suppose this is there. So if you want to find out gain, so it will be V0 by Vgs will be nothing but Gm Rd. So Gm times R0 parallel to Rd, assuming that RL is very large, load resistance is very large as compared to both of them, I get this into consideration. This is nothing but AV, voltage gain, right. So I get voltage gain, therefore AV for a common source amplifier is Gm times right Ro parallel to Rd, and therefore if you solve it, I get minus Gm times Ro Rd divided by Ro plus Rd. Is it clear? So if you want to find out the effect of Rd, for example, then just simply divide numerator and denominator by Rd, and you get what? You get minus Gm times Ro divided by 1 plus Ro by Rd. So if you increase the value of Rd, right, this quantity will decrease, and therefore this quantity will decrease, and therefore this whole quantity will do what? Will increase, and therefore gain will become larger. So therefore gain is directly proportional to Rd, as we have already learnt. Similarly, gain is also proportional to the value of Gm. Let us see what happens to Ro, right, we have already discussed. Again the same concept will come. If we divide by Ro, I get Gm times Rd divided by 1 plus Rd by Ro. So if Rd increases, this decreases, this decreases, this increases. So even if Ro increases or Rd increases, I will automatically get a higher gain with me, fine. So this is what we get overall gain, which you see. If you want to find out the overall gain, total gain of the system, then we write down Gv, which is the total gain, to be equals to Rin upon Rin plus R signal into AV, which is equals to minus Rg times Rg plus R sig signal into Gm times Ro parallel to Rd, right, and this therefore this gives you the value of your overall gain system. So this is the gain due to the device itself, and this is the gain due to the circuit itself, and therefore I get this. But as I discussed with you, overall since Rg is very large, this will cancel off with each other, and I will get overall gain to be equals to Gm times Rd with a negative sign because you will get a 180 degree phase shift between the drain and the gate of your device, right. What is your R out in this case? R out will be therefore equals to Ro parallel to Rd, right, and that is what we get. So with this information, let me see what we have understood till now. We have understood that the input resistance, right, in the CS stage is always equals to infinity, right, very important point, but it is infinity. Why is it infinity? And we have discussed this point just now. Why is it infinity? It is infinity because that you are applying to the gate side, right, you are applying to the gate side. Once you are applying to the gate side, gate is a open circuited. When gate is open circuited, you automatically get our input impedance to be infinitely large. Now, how do you define the open loop gain? So what I am trying to tell you is that for the gain, forget about open loop, let us just discuss the gain here. The gain of a CS stage is given as minus GM times RD parallel to RO, and output impedance is given as RD parallel to RO, right. So as I discussed with you, is ideally infinite input impedance is infinite, the output impedance is moderate to high, and the open circuit gain can be the open circuit gain can also be high depending on the value of GM, and the bandwidth of the CS stage is severely limited. We will not discuss this at this stage, but just for information's sake you can write down a term known as bandwidth of the CS stage is severely limited by capacitances. We will discuss this when we discuss the switching behavior, means we will go to frequency modeling of MOS devices. At this stage you can just keep this in mind that it is restricted. This will be this last point which is here, which is this one. The last point will be dealt when we discuss with you the modeling of the device for frequency modeling, high frequency, moderate frequency and low frequency, and there we will try to find out the bandwidth of the MOS device. But 3 things take away from all these discussion: infinite input impedance, moderately high output impedance, very large gain AV, and so on and so forth. Now as you can see, therefore the price, again the same thing as we had discussed earlier also, that let us suppose your RD is suppose your RO, right, is very large as compared to RD. Then I can safely write down AV 0 to be equals to approximately equals to minus GM times RD, because they are in parallel. And therefore again by the previous discussion, if I increase RD, I restrict my headroom, right, and therefore I am playing with there will be a chance of large order of discontinuity in the output side. Okay, so this is what the CS amplifier looks like, and let me come to the next stage, also referred to as, so this is what I was talking about. So you have your, just let me just come to the point. Let me come discuss the previous point as I was discussing with you. So so you see VGS equals to VI, so Rn equals to infinity, and therefore since Rn equals to infinity, I get VGS equals to V signal. Drain current is nothing but GM times VGS. This is the output voltage which you see, which is equals to nothing but GM VGS multiplied by RO, right. That is what is, because current multiplied by output impedance will be the output voltage, and therefore you get GM times VGS multiplied by RD parallel to RO is equals to VO, negative sign because gate and drain of a MOS device, between these two you will always have a 180 degree phase shift, right, phase shift you will always have, right, and that is perfectly plausible. Now this also circuit takes into account the R0 term, right, it was not there in the previous discussion. As you can see, this was there in the previous discussion, but so if you look at the previous discussion, this was grounded, whereas this is also grounded, but we have connected to the source end, showing that it is between these two nodes exactly which is happening. Now so this is what we get a common source configuration. Now let me come to the common source amplifier with the source degeneration resistance. So remember what change we are doing, what change we are doing is we are replacing the source side which was initially grounded by a source resistance RS, right. So there is a source resistance RS which is in series to the MOS device, right. So I have a MOS device here and I put a series resistance. I had discussed already with you why this is important in terms of application. See, it is important because as you make your RS large or you make your source degeneration resistance large, you end up having the voltage drop across this larger and larger, fine, because let us suppose current ID is flowing, ID is flowing. Once the ID is flowing through the circuit, ID multiplied by RS is basically the voltage drop across RS. So if your ID increases, right, ID RS increases and therefore this voltage increases, which in fact means that you are able to reverse bias this gate to source junction, fine. Why? Because it is an it's a MOS device, N channel MOS device. So this is basically N and this is basically P, you have an N region here, and since on the N side you are giving a positive bias, you are reverse biasing it. Once you are reverse biasing it, your current is falling down. So whatever current increase you got by virtue of some problem, you will be able to reduce it by doing a negative feedback, right. So this is also the negative feedback. Now Now so therefore, but then the idea there for the problem, what is the cost you pay for it is something like this. The cost you pay for it is now your leg room is restricted, leg room is restricted. Why? Because out of the negative, say you want to go to 0, you actually went to 0 at one point of time, IDRS is 1 volt. So IDRS, so out of 0 your 1 volt is already taken care of by IDRS. So you are 1 volt here. So you can only go up to this much point, you cannot go below this much point. If you go, you will have clipping, you will have wave shaping problems, so on and so forth. So this is with source degeneration resistance which you see, and I told you what is the advantage of source degeneration resistance, right. Let me therefore using source degeneration, so CS stage, CS with RS, let me just do some small derivation here. CS means the common source with source degeneration resistance. Now let me write down Vi, therefore again same thing, V sig signal into Rg upon Rg plus R sig, right. As I discussed with you, therefore Vgs is equals to Vi, and this is quite interesting, 1 by Gm upon 1 by Gm plus Rs. Now this is quite interesting, I will just explain to you from this discussion. See, now the idea is that if you go from this point to this point, from this point to ground, right, you are encountering two resistances, one is Rs, right, another is the resistance offered by this device, right, and that offer is that looking from the source side, the resistance offered is basically 1 by Gm. Remember Gm was equals to, Gm was del Id del Vgs, right. So if you do 1 by Gm, it is del Vgs by del Id, right. So del Vgs del Id primarily means that for the same change in the value of Vgs, how much Id is changing. That can only be done provided you know what is the resistance offered. So this is basically the resistance. So 1 by Gm is the resistance offered by the MOS device. So therefore this is very important, you can solve it yourself and get the principle, get this clear, that obviously therefore if you I can replace this Rg by 1 by Gm, Rg by 1 by Gm. So I am replacing this Rg by 1 by Gm, which I was assuming to be infinite in the previous case, I am assuming it to be 1 by Gm. Yes, 1 by Gm will be a relatively small quantity, and therefore Rs will be there here, and I will get something like this. Now from here this could be written as, or this could be written as, this could be written Vi upon 1 plus Gm times Rs, because if you cross multiply this will be 1 plus Gm Rs, this Gm will go in the numerator, right, and this Gm will cancel with this Gm and you will be remain with this. So I get what, Vgs equals to Vi upon 1 plus Gm times Rs, right. This is the gate to source voltage. Therefore I can write down Id, which is the drain current flowing through the device, to be equals to Gm times Vgs. Vgs is nothing but this quantity, so Gm times Vi upon 1 plus Gm into Rs, right. This is what I get, and therefore if I want to find out the value of V0 output voltage, I just have to multiply Id with Rd parallel to RL. So what I get minus Gm, right, into Rd parallel to RL output resistance multiplied by Vi, this Vi divided by 1 plus Gm times Rs, right, and therefore I can write down this V0 to be equal to minus Gm times, right, Rd parallel to RL, so V0 by Vi 1 plus Gm Rs. So if you solve it, I get minus Gm times Rd, assuming that RL is very large quantity as compared to Rd, I get 1 plus Gm Rs. This is your voltage gain. It is minus Gm Rd upon 1 plus Gm Rs. So you see, as compared to CS stage without source degeneration resistance, with source degeneration resistance your gain has actually fallen by a factor 1 plus Gm Rs, right, and that is quite an interesting observation, or quite an interesting idea, that what has happened therefore is that once you are increasing the value of a source degeneration resistance, because you want it to be more stable and you do not want it to be going beyond a particular limit, or you do not want to clip the output device, what happens is that this increasing Rs will result in a reduced value of AV, or the gain will reduce. right, and that is the price you pay for a reduced gain with higher RS. So, what we have learned therefore is that AV will be given as minus GMRD upon 1 plus GMRS, right. So, let me come to this point, and this is what I was talking about. So, AV 0 will be equals to minus GMRD upon 1 plus GMRS, and therefore, the resistance RS reduces the voltage gain by a factor of 1 plus GMRS. This is the reduction. You initially had GMRD, now it reduces by a factor of 1 plus GMRS. So, therefore, we define 1 plus GMRS is the amount of negative feedback which is introduced by RS, fine. So, you have a RS resistance, the voltage drop across it will be negative bias, reverse biasing your source to channel contact or source to gate contact, and as a result you will have negative feedback. This negative feedback will result in what? Will result in a reduced gain. So, what happens is the negative feedback is also known as source, this RS is known as source degeneration resistance, right, and the bandwidth increases by a factor of 1 plus GMRS. We will come to this later on in our discussion of frequency response. So, this is what we get from common emitter or common source with source degeneration resistance. Now, let me come to common gate configuration, and common gate configuration is again as I discussed with you, the gate will be actually grounded. So, it is also known as gate grounded configuration, right. So, this is also known as gate grounded configuration, right. So, I have a gate grounded configuration. What does it mean? That my gate is basically grounded, which means that my gate is grounded here, as you can see, and therefore, when gate is grounded we automatically have a device, and if it is an NMOS device it will be basically in a cutoff mode as such, and therefore, if you apply any signal here, right, what was the idea that VGS should be greater than VTH for the device to be off, but you see your gate is, you are giving a 0 voltage here. So, if your source voltage is positive, right, if it is positive gate voltage which you are giving, then gate to source voltage will always be negative, right, because let us suppose it is 2 volt here, maybe 1 volt here. So, 0 minus 1 will be equals to minus 1 volt, right, and therefore, you need to switch it on to give. So, but in the negative cycle, suppose this is 1 volt here, and in sorry this is minus 1 volt here, then 0 minus of minus 1 will be equal to plus 1, and this is larger than the threshold voltage. Let us suppose threshold is 0.7. In that case, this will switch on, and therefore, there will be a current flow, right, and so therefore, I have RD and so on and so forth. So, let me therefore delete this option here or remove all the inks here, and let me see for a common gate, if I have a common gate option, I will prove it maybe next time, that in this case also I get GMRD as my output resistance, but in this case quite interestingly you do not have a phase change of 180 degree. So, your output will be exactly in phase with the input side, unlike in the CS stage or in the CD stage, here you will not get the same profiling or same this thing in this case, right. So, with this let me stop here today and explain what we have done. Let me just recapitulate. We have done common source, we have done common source with source degeneration, we will take up common gate in the next turn and common drain in the next turn, and that will finish the amplification action of a MOS device. Since the MOS device is actually a device which is VCCS or a voltage controlled current source, our output impedance of the device will be typically low, but the input impedance will be typically very high, right, and therefore, I can use it in the MOS device provided I am able to fix it in the saturation region of operation of the device. So, with this let me thank you for your patient hearing. Until we meet next time, goodbye.